Hello and welcome to this new video. In this video, I'm going to cover section 1.5 about absorbing states and time of absorption. So this will finish chapter 1. In the next video, I'm going to solve the exercises. Okay, so we already encountered examples of absorbing states when we considered the random walk was absorbing boundaries. Right? There were two absorbing states. The snake ladder game has one absorbing state, which is the final state. So absorbing means that once you reach the states, you will stick there. Okay, so this means that the transition probability from an absorbing state to a self is 1. Okay, so now we will consider the case of a Markov chain whose state space can be divided into two parts. The set of absorbing states, because there may be, so there is at least one state, but there may be more than one, and the other are transient. Okay. Now, let capital AK denote the event of absorption in state K, and let QIK denote the conditional probability of being absorbed in state K starting from state I. And finally, let capital TA denote the time of absorption. This is, of course, a random variable in any absorbing state. Okay, and consider the mean time of absorption starting from state I. I call mu I. Okay, this is very important because many games actually possess some absorbing states, and we need to estimate the mean time of absorption or the mean time till the end of the game. So this was the case of the snake ladder game. Okay, so I asked you to do some simulations to estimate in how many moves on average the game will end. How many moves do we need till the end of the game? Of course, it's a random variable, but it possesses a mean. Okay, so it turns out that these probabilities and these mean times, conditional mean times, satisfy a linear system of equations that we can easily solve usually. So the first equation, so it's actually a system. So QIK is PIK plus the sum over all transient states of the transition probability from I to J times the probability of absorption in state K starting from J. Okay, and you have a similar sum to mu I satisfy the linear system 1 plus sum over all transient states of Pij mu J. Okay, now the derivation of the first formula is easy because it's just a consequence of the total conditional probability formula. Okay, conditional total probability formula. The proof of the second one is a little bit more difficult, so I will not. So you can always find such equations, and it's advisable actually, but this is one of the rare places that I will ask you to memorize this simple formula. It's not difficult actually, because if you want to prove it every time, it's a bit cumbersome. Okay, so, and now I will illustrate the use of these probabilities on examples. Okay, so let us prove. Okay, now before I go to the proof, let me just give a remark. If I is an absorbing state, then of course QII is 1 because we are already there. So and the mean time of absorption is 0 because we are already there, so there's no move. And also, if there is only one absorbing state, then for all states I, QIK is 1 because you are going to end in an absorbing state ultimately. Okay, so when there are absorbing states, sooner or later, ultimately, the game will stop. Okay. Now, it may take a long time before it stops, but ultimately it will stop. Okay, with probability 1. Okay, proof. So I just tried the conditional total probability formula, and I condition on the first transition. So x1 equal j. And now I split my sum into two parts, the sum over the absorbing states plus the sum over the transient states. Okay. Now, okay, if you look at this transition probability, we can, so the Markov property tells me that so this is past, present, future, right? So we can eliminate the past given the present. So the first sum can be written as PIK given x1 equal j, and this is just the transition probability from I to j. Okay, and similarly for the second sum. Okay, so this is the Markov property that tells me that I can eliminate the past given the present. The present here is x1. Okay, now look at the first sum. Here in the first sum, j is absorbing and k is absorbing, right? So if j equal to k, this is just 1. If j is different from k, this is 0 because we have two distinct absorbing states, so we cannot move from an absorbing state to another one. So it's 0. So I denote this by delta kg. So this is the canonical delta. So it's 1 if k equal j and 0 otherwise. So the first sum is actually just PIK because there's only one term surviving, which is PIK. And yeah, sorry, there's a Q. This is a QIK, not FI. And if I look at the next term, I see that this is just QJK, right? So I get this first. This is the system actually. So it's very easy to prove. Okay. So please correct that. This is QJK by definition. Earlier, I denoted it by FJK, but in order not to confuse with the FII that I used in a previous video, so it's better to denote it by QJK. Okay. Okay, now the second one is a little bit more involved. So also I can apply the total expectation, total conditional expectation actually. So I do the sum and over all states, then I split into the absorbing states and transient states. Now, if you consider the first sum, j is absorbing, okay? So therefore, with probability 1, TA equal 1, okay? Because this is the mean, so there's only one step here, okay? So it means that, so here actually j equal, so from x0 equal I to x1 equal j, there is only one transition. And if j is absorbing, it means that the system made exactly one step, one move. So TA is 1. Okay, so the expected value of TA given these two is just the probability of TA equal 1. And this happens with almost surely, so with probability 1. So the system made exactly one transition before reaching the absorbing state j. Okay, so this is actually done. Now, for this next sum, I need to prove a claim that you may understand on a conceptual level. So the estimated, the average time of absorption starting from x1 equal j is 1 plus the same mean starting from x0 equal j. Where does this 1 come from? It comes from the transition from x0 to x1. Okay, this is actually by homogeneity. This is a consequence of homogeneity. You may have encountered this before. So when I do one step, I have to add 1 the mean time. Okay. Now, if you understood it, then fine. If not, we can prove it directly. Okay. So, but first note that the probability that we have absorption in n steps starting from x1 equal j is the same as the probability of n minus 1 moves starting from x0. Okay, so because these two probabilities express the same thing. It's the probability of being absorbed in n minus 1 transition starting from state j. Okay, this is a consequence of homogeneity, if you like. Okay, and now I condition actually on, so I go back to the definition, if you like. So TA can take any number of values, so from 1 to infinity actually. So by definition, this is the definition of the expectation of a discrete random variable. Okay, but the probabilities are conditional on x1. So n is the value taken by TA, and this is the probability of TA taking values, but everything is conditional. And now I apply the remark that this transition in n steps is actually a transition in n-1 steps starting from x0, okay, by homogeneity. Okay, and now I do a change of variables. Instead of n, I put n plus 1, and I start my series from 0. So it's just the same thing. And now I split it into two parts. Okay, the sum of m and the sum over 1. So I split it into two because I divide. So, okay. Now, once again, the first series is actually the conditional expectation of TA, right? And the second series is when I do the sum, actually, is just the probability that TA is finite starting from x0 equal j. Okay, and this probability is actually 1 because the probability that TA is finite is 1 because there is an absorbing state at least. So with probability 1, the game will end. Okay, so this proves the claim that when I condition on x1, I have to add 1 to the expectation. Okay, and this one comes from the fact that there is an absorbing state, and so sooner or later the game will end. Okay, now it's easy, having proved this claim, it's easy to go back to equation 1. Yeah, so I go back to this, and I apply this formula. So I just replace this formula here. Okay. And this is 1. So the first sum will be sigma of Bij, and the next one I have to add 1. Okay, so that's it. So just replace. And so I have once again I can split this into two, sum of Bij over T, and when I combine it with the sum over the absorbing state, I get sum over all states, which is 1 because it's a probability. And you are left the sum of the expected values, which is mu j precisely, and that's it. So note that we have to sum over only the transient states, not all states. Okay, so as you see, this formula is a little bit cumbersome to prove every time. So I will ask you to just memorize it, and now we'll illustrate the use of this on an example of a game. So consider this very simple game. So when a player flips a fair coin, until 3 consecutive heads appear. Okay. So, and we want to compute the mean number of flips until the end of the game. So it's like the snake ladder problem. Okay. But in order to answer this question, we have to model the situation with a Markov, with a homogeneous Markov chain. So sooner or later the game will end, but so it could take a long time. But what is the average of the number of times? The number of times is a random variable, and we are interested in the mean time till the end of the game. Okay. By the way, if you are bored, try this game so many times. Okay, and each time record the number of. So repeat it at least 15 or 20 times, and then take the average. Or better, do the simulation with the computer. Okay. Now, if you want to model this by a Markov chain, denote the state T, the tail by T and head by H, and X and any event head or tail. So there are 4 states in this Markov chain. State 0 will be, so what does it mean? This is the last 3 steps, the last 3 flips. So consider the state. Anything, the last flip is tail. Okay, what is the probability of this, of being in this state? It's just 1 times 1 times 1/2, because they are independent, right? So I consider only the last 3 flips. Okay, so if the last one is tail and the other 2 are arbitrary, I denote this by state 0. Now, if the last flip is H and the one before is tail and the one before is arbitrary, I call this state 1. And this happens with probability 1 times 1 over 2 times 1 over 2, which is 1 over 4. Another state will be tail head head, and this happens with probability 1 over 8 because 1/2 times 1/2 times 1/2. And finally, we have our absorbing state, which is 3 consecutive heads, head, head, head. And this happens with probability 1 over 8. Okay, now let us compute the transition probabilities between the states. Okay, if you are in state 0, so the last one is tail, where could we go? We can go to state 1 actually if we had H, and this happens with probability 1/2. Or if we have another tail, we remain at state 0. So we have two possibilities. Suppose now that my third flip is tail. What about the fourth time? If it's tail, I go back to state 0. If it's head, I move to state 1. It's very interesting. This is a problem of modeling, actually. So that's it. So this is from state 0. We can either state in state 0 if we have another time t, or we move to state 1 if we obtain head. Now, if you continue this reasoning, you will convince yourself, try to do that. I'll not write the details. Okay, so from state 0, we can either remain at 0 or we move to 1. From state 1, we can go back to 0 if we obtain tail, or we go to state 2 if we obtain head. So it's 1/2, 1/2. State 2 is similar. So either we go back to state 0 if you get tail, because you get HHT, or HHH, and then we move to state 3. And from state 3, we are done. Okay, so we have now a homogeneous Markov chain on 4 states. And it's very easy to draw the graph of this. I will not do it, you do it. But this is the transition matrix. Okay, so now we can apply the previous result. If you consider mu 0, so I equals 0 here, so we have to add 1 plus the probability of going from 0 to 0 times mu 0 plus the probability of going from 0 to 1 times mu 1. Same, so it's very easy. So just, yeah. Now next, the mu 1 is 1 plus the probability of going from 1 to 0. From 1 to 0, it's 1/2, plus the probability of going from 0 to 2 times mu 2, right? And the last equation, mu 2 is 1 plus 1/2 times mu 0. Okay, we don't count this because this is an absorbing state, so only the transient states count. So there are 3 transient states and 1 absorbing state. So these are the equations for mu I. Of course, you can add mu 3, but mu 3 is 0 actually, so it doesn't matter. You can solve this linear system in any way you like. I don't impose on you any special method. You can use the Gauss-Jordan elimination. You can use matrices. You can do substitutions, anything you like. But when you solve it, you will find these values. So mu 0 is 14, mu 1 is 12, and mu 2 is 8. So what does this mean? It means that starting from state 0, on average, we need 14 moves or 14 flips to end the game. If you start from 1, so are closer, we need less, we need 12. And if you start from state 2, we need, on average, 8 moves to finish the game. Now, these are conditional expectations. If we want the unconditional expectation, okay, so we have to multiply by the probabilities and add 3, because note that we have to flip at least three times the coin to start the game. So we have to add 3, okay? And then we multiply the mean time by the probability of starting at 0, which is 1/2. We have to multiply mu 1 by the probability of starting at 1, which is 1 over 4 as we obtained, and so on. So we also get 14. Okay, so this means that we need on average 14 flips to win the game. Okay. There is a similar exercise that we shall solve later in the exercises. And now let me finish this section, and this chapter was something about the gambler's ruin problem, where we have actually here two absorbing states. Okay, so it's a random walk, as we know, and we have two absorbing states, 0 and n. So either the gambler is ruined or he has a fortune of n, and then he quits the game. Okay, this is the rule. And we have, of course, a probability of winning, P. Okay, so you can interpret this as in two ways. So either you consider a random walk was absorbing boundaries, or a gambler having a probability P of winning $1 and 1 minus P of losing $1, and then he quits when either he is broke or he has a total fortune of n dollars. And we can easily compute actually the probability of absorption in state n. So the probability of winning the game, or winning the game with n dollars, a total fortune of n, starting from state I. So we have these formulas. And we have also something similar to estimate the mean time of absorption in state n. Okay? And let me give you an interpretation of these results before I prove them. Okay, suppose that P is less than 1/2 or equal. Okay, so it's 1/2. What happens as n tends to infinity? If n is big, so the interpretation, if a gambler is playing with a rich adversary or a casino, then n is big. So when n is big, this probability tends to 0. Okay, and if P is less than 1/2, we have the same thing. Why? Because if P is less than 1/2, then Q over P is bigger than 1. Okay, 1 minus P over P is bigger than 1. So Q over P, so I can write this as Q over P, or 1. So Q is 1 minus P, right? So if P is less than 1/2, then 1 minus P over P is bigger than 1. Okay, so the ratio tends to infinity. Okay, what happens if the ratio tends to infinity as n tends to infinity? So yeah, so the denominator tends to infinity, and therefore the ratio tends to 0, right? Because I have a number over infinity. So Pi as n, when n is very big, these probabilities are very small, right? This is what the takeaway actually from this formula. You don't need to remember the formula. I'll not ask you about it, but this is just a mathematical study of gambling, if you like. So, and by the way, this is why probabilists and mathematicians usually do not gamble, because they know that the probability of winning is very small, and therefore the probability of losing is very high, right? Especially if you are playing against a rich adversary or a casino. Okay. Even if the game is fair, right? Even if P equal 1/2, the probability of losing becomes very high. So maybe you win once or twice or 3 times, but statistically you lose most of the time, and this is very bad actually, because you may lose everything. Okay, now why this is so? So I just need to change it a little bit. So we can all apply the first proposition of this video, but it's a little bit simpler to reason directly by applying the total probability formula and by condition on the first transition. Okay, so what is the probability of being absorbed in state n, the state of winning here in this case? So I apply the total probability formula. Okay, so I condition on the first transition x1 equal I minus 1 times the probability. So because from state, if you are in state in state I, then we either can go to state I minus 1 or go to state I plus 1. Okay, so either we win or we lose because it's a random walk. Okay, now if you look at the first one, by the Markov property, this is just the probability. So this transition probability is just Q because I move from I to I minus 1. This transition probability is just P because it's the probability of winning. This probability P of A, given that x1 equal I minus 1, by the Markov property, I can eliminate the x0. And this is just actually the Pi minus 1, because this is the probability of winning starting from I minus 1 by homogeneity. And this probability P of A, given that x1 equal I plus 1, is the probability of winning or being absorbed in state N starting from state I plus 1. Okay, so I get this recurrence relation between Pi minus 1, and Pi plus 1. Q and P, small q and small p are given actually. Okay, and so this is what we call actually a finite difference equations, and of course we need to add the boundary values. So P0 equals 0 if we start from after 0 is absorbing, so there's no chance of going from 0 to n, and if you start at n, we are done. So okay, and so we need to solve the system of equations, these boundary conditions, and I will present here. So in principle, you already know the theory of the linear difference equations. You just solve the characteristic equation. You find the characteristic equation. It's like differential linear differential equations actually. But we can solve it in an elementary way. So just rearrange this equation and write it in this way. Small p, pi plus 1 minus pi is q pi minus pi minus 1. Okay, because because I have pi here, so I split it, and p plus q equal 1. Okay, and if we divide by p, we get this relation. What does this mean? It means that the sequence pi minus 1 is a geometric sequence with ratio q over p, because each time I multiply by q over p. So since p0 equals 0, the first equation tells me that p2 minus p1 is q over p times p1. The second equation, we multiply the first one by q over p. So we have q over p squared. And if you continue at the ith step, we get pi minus 1 is equal q over p to the I minus 1 p1, and so on till the last term. Okay, so this is very elementary. And therefore, when we sum the first I equation, so if you sum these two, we have cancellation. P2 cancels with P2, so we are just left with what? With Pi minus P1. Okay, and I do the summation. There is a formula for this. This is just, so now we have to distinguish between two cases, because the ratio could be equal to 1, could be or less than 1, right? Or bigger than 1, we'll see. So if P equal Q, if the ratio is 1, it's very easy actually, because this is just a summation. So it's I plus I minus 1. So it's I. So we get Pi equal IP1. Okay, and for every I. So in particular, Pn is NP1. But since Pn equal 1, we get P1 equal 1 over n, and so Pi equal I over n. So this is very easily solved. Okay, this is the fair case. Okay, it's the symmetric random walk. Now, if Q over P is different from 1, so P is different from 1/2, there's a formula for this. Okay, it's the sum of r to the k from 0 to I minus 1. So it's 1 minus r to the I over 1 minus r. Okay, so we get easily this relation. And that's it. So in particular, we get the formula for Pn. And now we use the boundary condition, Pn equal 1, and we find that Pi is equal to this ratio. Okay, so this is just algebra. Okay, so once again, you are not obliged to memorize these formulas. Okay, and now The second part actually is a little bit more tricky. Well, a little bit, because you have a constant term here. Okay, so we can solve it, if you like, with the same method here, okay, by using geometric sequences, or, which is better, if you know the theory of linear difference equations, what do? It's very easy. First, you solve the homogeneous equation by finding the characteristic equation, okay, and then you find a particular solution, and then you add them. Okay? It's like you do with differential equations, okay, and we use these boundary conditions. I will not do it. If you are interested, you can do it. And once again, the formula for the second part, okay, you don't need to memorize it because it's a little bit complicated. Okay, but this is to tell you that there is a formula for the mean time of absorption in state n. Okay, so this concludes this video and chapter 1. In the next video, I'm going to solve the exercises of chapter 1. So thank you for your attention and see you soon.